Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with another geometry video for you all. Today's lesson topic is all about polygons and symmetry. We're going to go into depth all about specific polygons and how to discover their symmetric properties. But before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our latest posts at eCoreAcademy. It's all very much appreciated. As I was saying, our topic today is polygons and symmetry, and the whole theme and purpose of today's lesson is going to be it's going to be about discovering and determining the figures, lines of symmetry, and all of a polygon's similar properties. So what that basically means is if we're taking any figure existing, we're going to try and identify whether or not it's a polygon, and we're going to see what specific type of polygon it might be, and many of its different properties as well. And then we're going to further establish some symmetric properties. And if you don't already know what symmetry is basically a property in which one side of a figure or one side of any shape, let's take, for example, the human body, looking at it straight up. If we split it from the vertical axis, if we split it down, what happens is you take both of those sides and you're looking at those sides, and they're basically identical, and they're put right next to each other. And they're also identical. They can also be proved to be congruent as well, which is equivalent. If you flap one on top of another, and they map onto each other directly, so that proves direct symmetry. And the human body is just one way to actually exemplify that. Unless, of course, you're missing a limb or something, well, then I can't really prove that your body is going to be symmetrical all the way down, but I can if you have all of your extremities. So let's move on to the lesson. So our first slide here is going to be about polygons. So we're going to just review what polygons are before we start getting into higher level concepts and higher level types and classifications of polygons. So let's start off with a basic definition of polygons. So a polygon is a closed figure formed by 3 or more line segments in a plane, such that each line segment intersects exactly 2 other line segments at their endpoints only. So I know that's a bit of a wordy definition, but it has a very simple reference source to it. So I'm sure many of you have either heard of a polygon before or have seen one before. You know all of your polygons by now. It's basic shapes. So I'm going to give you an example of what a polygon that you probably know is. So first one here is going to be a triangle. I'm sure that you've heard of that, a triangle. It has 3 sides and 3 angles. And then we have a square here. Square, and the square has a measurement with 4 equal sides and 4 right angles, or 4 angles, so 4 sides and 4 angles. And you can have another object such as a hexagon. A bit more complex, just a bit more sides, but it's very similar. Actually, let's refer to something a bit more simple. Let's refer to a pentagon, which is going to be 5 sides. So that's 1, that's 2, 3, 4, and 5. So that's your pentagon right there. I'll write that down here. So a pentagon has 5 sides and 5 angles. So these are common examples of polygons that are existent in our geometric concepts, and I'm sure you've heard of all of these. Probably most likely you've heard of all of these shapes here. So a polygon, like I said, is a closed figure formed by 3 or more line segments. So what that basically means is that a polygon must have a minimum of 3 line segments, which represent its sides. So it has to have a minimum of 3 sides, and that's represented by a triangle. The reason it cannot have 2 line segments or 1 line segment is because it's impossible to make a figure with with all closed sides. That means it has some kind of closing off without an open space intersecting one of its line segments. So you must have a minimum of 3 line segments to have a closed figure, which is a polygon. And it exists on a plane, which basically means that it's a 2-dimensional figure, and such that each line segment intersects exactly 2 other line segments at their endpoints only. So what that means is, if you're taking, let's just look at the circle here, and the circle, I'm going to magnify that. So if you're having one line segment here, it must intersect at 2 other line segments at vertices or points of common intersection. So that means this line segment A, has to intersect two other line segments at a common point called your vertices. So that's also a very common point. It's where two line segments meet. It's a common point where two line segments meet, and that is your vertex. And vertices is a plural form of vertex. All right, let's move on. And like I said, the vertex is the point in which the segments meet. Let's look at types of polygons now. So now that we've got a basic understanding of what polygons are, now we've refreshed that since that's a very basic term that you're already expected to know. Let's start classifying our polygons. So let's look at our first two types of polygons, which are convex and concave polygons. And let's look at convex polygons first. And if you couldn't tell already, convex and concave polygons are going to be direct opposites. So a convex polygon is a polygon in which every line segment, that should be segment, not segments. I apologize for that. Polygon in which every line segment connecting any 2 points inside the polygon lies completely inside the polygon. So if we look at our pentagon here, we can use this as an example. So I'm just going to label this as our pentagon, just in case you don't know what that is. And you're not expected to know that in this lesson yet. But if we look at this pentagon, it's actually going to be a convex polygon because of the fact that if you take any 2 points, if you take a point, you say, for example, we're going to label this point here A, and you label another point here B, what it's saying is it's a convex polygon if you can connect this point A and point B with this entire line segment AB being on the interior of this figure, meaning the line segment does not merge or go over any of these side lengths of the convex polygon, meaning that it will always stay inside. So if you connect any 2 points on the inside of a figure, in a convex polygon, the line segment will always remain inside the figure as well, and that's not the case for a concave polygon. So in layman's terms, basically, generally what you can say a convex polygon is basically a polygon that has all sides that are not caving inwards but are always pushing outwards. I mean, it has defined vertices that are pushing outwards from the center and none of which are pushing inwards. And all of the relations will always be outwards and inwards, meaning that there will always be a consistent push outwards in a convex polygon. However, that is not the case for a concave polygon, because a concave polygon is a polygon in which at least one line segment that connects any 2 points inside the polygon does not lie completely inside the polygon. So this is an example of a concave polygon, because if I were to put a point here, label that point A, and label this point B, if I connected them, the line would actually exist on the outside of this polygon. So basically what happens is this is an inverted form of a polygon. And of a convex polygon. So we can think of this as a polygon, a convex polygon has exverted, meaning outside or exterior pointing points that do not point inwards. Instead, they always point outwards from the center of the point of the figure. But a concave polygon will have at least one point that will be pointing inwards with its vertices digging inwards. And as you can see, it's called concave because it almost caves into the center, while convex actually exits outwards from the center and with the same exact direction, meaning all of these line segments will be pointing outwards and all of these vertices will be pointing outwards rather than inwards. And finally, let's look at polygons of symmetry, our last type of polygons. And the polygon of symmetry that we're going to look at here is a regular polygon. And a regular polygon is a polygon that is equilateral and equiangular. So the reason that I subtitled this slide as polygons of symmetry is because regular polygons are the only types of polygons that actually have symmetric properties. So symmetry is basically when, in layman's terms, it's when two halves of a figure, any two halves of a figure can flip over each other, mapping perfectly. Just as I had shown you that example at the beginning of the video. So that's a basic definition of symmetry. Mapping over each other, mapping perfectly. So that's what regular polygons are. So basically what a regular polygon is an equilateral and equiangular. So what that means is equilateral stands for equilateral means all equal sides. and equal angular is all equal angles. And some common examples of those are, your squares, because they have all equal sides and all 90-degree angles. Also, you have equilateral triangles, which have all equivalent sides and three 60-degree angles. So those are two common examples of regular polygons. Now let's move into angles. Angles and polygons. We're just going to briefly go over this because it is important to cover this in this topic, because we're actually looking at polygons as a whole and their different properties. So an interior angle in a polygon is any of the angles inside a polygon, and the exterior angle are any of the angles formed by two sides of a polygon in which one side extends outwards. So I'm going to show you what that looks like here. So an interior angle, say for example, we're going to draw a square out here. Let's draw it out here. We draw a square here. It's basically all of the angles on the inside of the figure. So there's 4 angles on the inside of the figure. And the interior angles is equivalent to the amount of side lengths that that any figure that you're given has. So since a square has 4 side lengths, for 4 sides, it will always have 4 angles, and those angles are at the inside of the intersection of line segments. But the exterior angle is when you take a figure like a pentagon in a regular polygon, and what you're going to do is you're going to take each of the line segments, each of the sides, and you're going to extend them out infinitely. You're just going to extend them out. And what happens is, after you extend them out, like this, each side is extended out separately. What happens is you're going to form a little angle here, and this is on the outside of the figure. And that will be considered your exterior angle in a regular polygon or any polygon. Let's move on to the angular equations revolving around interior angles. As we mentioned, interior angles, I'm going to give you a little equation here that you can actually use to solve the measures of interior angles in any polygon, in regular polygons. So to find the measure of the interior angles in a regular polygon, use this formula, and keep in mind only for a regular polygon. It's just that the interior angle equals 180 degrees times n minus 2. So if I were to give you this triangle here, you would use this formula. You would want to, say for example, you'd want to calculate one angle in this triangle. Since we know that all regular polygons are equal angular, meaning they have all the same angle measures, you can just calculate one to find all of the others. So what you would do is you'd plug in this equation. So you'd say I equals, I being the interior angle measure, equals 180 degrees times n minus 2. And n stands for n equals number of sides. So basically what that's saying is, if you want to calculate, sorry, I apologize, it's the sum of the interior angles in a polygon, and that's all you need to know. That's what I was trying to say. You only need to know the sum of the interior angles of any regular polygon, because if you know the amount of angles within that polygon, you can simply divide it, since we know that all angles in a regular polygon are equivalent. So what you're going to do here is you're going to calculate the number of sides in a triangle, and that's 3. So you're going to sub 3 minus 2 equals 1 here, and you're going to multiply 180 degrees times 1 to get 180 degrees. And that is always true, since a triangle has 180 degrees total for the sum. And this is not used for, your basic figures that you already know. This is used for those regular polygons that are like 16 sides, 18 sides, 20 sides that you might not be familiar with. But this equation will always be true for any type of regular polygon with n number of sides. And now let's look at the angular equation for exterior angles. So to find the measure of the exterior angles on a regular polygon, use this formula. So all exterior angles will always add to 360 degrees in any figure, and that's what this equation is revolved around. So all you're going to do is you're going to see that you have 360 degrees, and all you're going to do is you're going to divide it by the number of sides that you have. Since all those side angles add to 360 degrees, and since the number of sides is always equal to the number of angles in any instance, even if it's an exterior angle or an interior angle, you're just going to divide 360 by the number of sides. So we're going to refer back to this pentagon here that I showed you as an example in the previous slides. So what we're going to do is we're going to take this pentagon. We see that it has 5 side lengths that actually extend outwards from their original position. And if you look at each one of those side lengths, you can count them out. They have 5, and you're going to divide 360 by 5, since we see that's the amount of sides that this pentagon has. So if you divide 360 by 5, we can do our long division here. 360 and 5. 5 goes into 36 7 times. So 35 minus 1 and then 10. And 5 goes into 10 2 times. So we're going to have 72 degrees as our exterior angle. So that's going to be the value of this exterior angle here for all of them, since they're always going to be equivalent as well. So now let's finally get into our polygon symmetry. This is more of our symmetry part of this lesson. So let's look at the basic properties of symmetry. So reflection symmetry, which is basically another way of expressing symmetry, is a characteristic of a figure in which it may have at least one axis of symmetry when the figure is reflected. It can be folded along an axis of symmetry and both halves will match up. So basically what it's saying is, if you're given any figure, if a figure has reflection symmetry, it means it can have an axis of symmetry, which is a line that splits it equally on any line, any part of the figure, and what will happen is that figure will actually overlap, flip over to be completely equivalent. And some regular polygons actually have more than one line of symmetry, but all regular polygons have at least one line of symmetry, or one line of symmetry. So if we're looking at a square here, basically what that means is, if you're given, or I already have a square drawn here, or a square pictured here, so I'm just going to erase this. So if you look at the square, what you can do is you can draw some lines of symmetry. So I'm going to draw this line here. And what happens is, you're going to take this side here, right here, and you're going to flip it over to this side here. And when you flip this side over, it'll match up perfectly, and it'll look just like this. It'll look, oh, well, that's really off. Excuse me for that. It'll look just like this here, which is exactly 1/2 of that square, which is basically a property of symmetry. So you're basically cutting it in half through an axis of symmetry, and you're taking one side and you're flipping it onto the other side so that it matches up completely without any protrusions. It'll match up completely, just like your hands too. I can show you that as an example. They map onto each other perfectly. Polygon symmetry part 2, let's look at the actual process in which this is done and calculated. So the axis of symmetry is a line drawn through a figure so that one side is a reflection of the image on the opposite side, also called the line of symmetry. So in order for a figure to have reflection symmetry, it has to have at least one axis of symmetry, and every regular polygon has at least one axis of symmetry. So if we're looking at this square here, like I said before, it's basically any line that splits a figure and in half, and can flip it over in such a way that it overlaps the other side. So like I just showed you, so these are the 4 lines of symmetry for a square. I'm just going to write that down. This is a cool fact to know. These are the 4 lines of symmetry for a square. And if you fold it on any of those sides, you will see that they will match and map onto each other perfectly. So square equals 4 sides, or 4 lines of symmetry. 4 lines of symmetry for this square here. All right, let's move on to our final side, Polygon Symmetry Part 3, and this is the laws of symmetry. So these are the applications and the rules that you must follow, the code of conduct. So this is basically our theory-based propositions. So all regular polygons have at least one axis of symmetry, so that's one law. And the number of lines of symmetry on a regular polygon is determined by the number of sides it has, which is basically stating that the number of sides equals the number of axes. So if you're given any figure, or any regular polygon, the number of sides, the number of axes that it has is determined by the number of sides that it has. So say, for example, we're given a square here. So a square has 4 sides. Therefore, it has 4 axes. of symmetry. And if you're given a triangle, an equilateral triangle, and you think about an equilateral triangle, you might be thinking to yourself, well, how exactly will it have three axes of symmetry? Well, that's always going to be true. So it'll have three axes of symmetry. Because if you're looking at an equilateral triangle, which is all equal sides, you can split it down the middle, across from this vertex to this vertex. It will match up, and this side to this side. So they will always have the same maintaining equivalent ratio. Alright guys, so that's the end of today's video. I hope you guys enjoyed. This has been eCoreAcademy e-learning platform today. Please make sure to like and subscribe down below and hit the post notification bell to get notified on any of our channel latest posts. Visit our website at eCoreAcademy.org, which is very up and coming. We have all full unlocked access to all of our videos, as well as integrated quizzes, note sheets, and worksheets that go along with each and every single video, organized into our course studies by each and every subject. And please feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. Visit all of our socials in the description box below with all of their links at Facebook, Twitter, and Instagram to see what kind of content we have there, and if you want to share all of our videos to friends and those who may need help. And feel free to comment down below with some constructive feedback, or if you just want to reach out to us, just like our email is always open. So I hope you guys enjoyed this video. I had a pleasure making it. It's been AJay Raj, and I will see you guys in the next one. Peace.